Okay, chapter 6, section 1. It's the right triangle approach to introducing what the field of trigonometry is. Okay, so it should be a very simple section. We'll fly right through it, I hope. Chapters 5 and 6, I think most students agree, are fairly easy. It gets a little harder in chapter 7. Still in the field of trig. But chapters 5 and 6 are usually pretty easy. We're going to look at angle measures, angles in standard position. We're going to define a bunch of stuff. Lengths of a circular arc. We're going to look at the area of a circular section, and then look at circular motion. Okay. So angle measure. Simple definitions. An angle, AOB, consists of two rays, r sub 1 and r sub 2, with a common vertex, O, as in the figure, right? So it's just two rays. A ray is, we have a line. A line goes infinitely in both directions, right? Just some definitions of things. Right? If we have something like that, with this little arrow indicating that it goes on forever that way, and then goes on forever this way, that's a line, right, in both directions. If on one side it terminates and on the other side it goes on forever, that's a ray. And then if it terminates on both sides, then we call it a segment. Line segment. Okay, all right, so we have two rays. We have ray sub 1 and ray sub 2. And then the side that terminates coincides for both of them. Okay, exactly what we thought it would be. Pretty obvious description of what an angle is. Okay, so here is an angle. It's got an initial side, and then it's got a terminal side. So we like to keep the initial side fixed so we don't move it. And then we like to move around the terminal side so that this thing can go, up and down, kind of change it up and down, so that we can have another angle that goes all the way out here or goes all the way out there, right? So it can go in different places, and also it can come down here. So we move around the terminal side to get different angles while we leave the initial side alone. Good, obvious, easy, right? Good. Okay. In this case, R1 is called the initial side, R sub 2 is called the terminal side. If the rotation is counterclockwise, the angle is considered positive. And we're going to have to come up with some other way of describing what these motions are, since I think increasingly people are unaware of what a clock is, or a traditional clock. So clockwise and counterclockwise, right? The old school kind of clocks. We have a circle, and we have little things that point to the time, right? So we have noon is up here, 1, 2, 3, right? And so the clock hands go in this direction. So when you move in this direction, we call that clockwise. Clockwise. And then when you move in the other direction, we call that counterclockwise. You go in that direction. That's counterclockwise. Good. Okay, so counterclockwise is an angle that's considered positive, and clockwise is the direction we consider to be a negative angle. Okay, hopefully that's pretty familiar, right? I'm like I said, we're going to fly through this quickly, since I'm already assuming that this is really just a review of trigonometry for people. Okay, the measure of an angle is the amount of a rotation for the vertex required to move R1 onto R2. So intuitively, this is how an angle opens. One unit of the measurement of the angles is in degrees. So that's one way that we can describe how wide the angle is. And almost arbitrarily, it's sort of mysteriously why, no explanation given, we've chosen one full rotation to be 360 degrees. I'm sure we can find some sort of historical sort of reference for why that is. I think it's credited to the Babylonian Empire, and I think the Babylonian Empire, their math really liked the number 60. It has a lot of nice properties, divisible by a lot of things. They really liked it. I'm pretty sure they have a base 60 number system. I'm not really sure about that. But anyway, so I think they're credited with this this idea of creating degrees, and they've chosen 360 because again it has a nice multiple of 60 and divisible by lots of numbers, and so for various reasons they've chose 360, and it's just kind of stuck with us over time, right? But it's a little arbitrary. I mean, you could have chosen 500. Why wouldn't 500 be one full rotation, or 1,000, right? So some of these things are just sort of historically connected to things, so they're kind of interesting to look at. Anyway, so degrees, 360 degrees is one full rotation. So 1/360th is 1 degree, and then that indicates a movement, a certain size of an angle. The other way to measure the angle is through something called radians, which we'll spend a little more time on, but this has a slightly more mathematical sort of reasoning for why for why we use it and how it's defined. Good. So those are the two we're going to be working with: degrees versus radians. Good. Make sure you stop me if you have any questions on anything. Radians. So how are radians defined? So radians are defined by using the unit circle. That's important to remember. It's the unit circle, which means it's a circle with the radius is 1. Good. And then we have some angle theta. Good. Okay, so a radian is defined as the distance around the unit circle that is described by the angle that we're trying to identify. Good. So in a unit circle, radius 1 drawn with the vertex of an angle in its center, then the measure of the angle in radians is the length of the arc that subtends the angle. Good. Subtends, that's the word I was looking for. So if we measure this distance around here, then we define this theta to be that distance. Good. Questions? So a radian, is a distance around the unit circle. Questions? So here's some classic ones. So remember that the entire distance all the way around the circle, right, if we define this to be this way, means that if we have a circle, here's a circle, the distance all the way around is the circumference of the circle. This distance all the way around, given that this thing it's the unit circle, so that means that this distance right there, r, equals to 1 on the unit circle. So the circumference is equal to the formula 2 pi r. Of circle is equal to the formula 2 pi r, but in this case, since r is 1, then the distance all the way around the circumference is just going to be equal to 2 pi. 2 pi is the distance all the way around. Good. Okay, and remember, pi is approximately, pi is approximated by 3.14. Let me know what this is going to go to. It's approximately 3.1415926, right? And it keeps going on forever. Never repeats. The pattern, a pattern never emerges. But usually we round it to about 3.14. So if we leave it about 3.14 and we multiply it 4 and we multiply that times 2, we get 6.28. So we can say this is approximately 6.28. Good. So it's a number that goes to from 0 all the way around to approximately 6.28, and those are that's how we describe radians in that range. So here's some easy classic examples of a radian to describe an angle. On the unit circle, if we have this distance right here, it's got a distance of 1, right? If we took a measuring tape and we measured it in terms of whatever units this was measured in, right? So if this is centimeters, then this is 1 centimeter. Or if this is feet, then this is 1 foot. Power. If this is meters, then this is 1 meter, right? So whatever units they are, if they're the same units, if we take a measuring tape and measure the circumference distance around here, then that distance is how we would define what the angle is. So this is an angle of 1 radian. It equals this, right? An angle of, now because the circumference all the way around is 2 pi, then half of it would just be pi. And so we could also say that this is about 3.14 units, right? If it was feet, if it was meters, whatever unit you're using for your unit circle, it would match the units that you use to measure all the way around. And so half a circle would just be approximately pi. Good. Questions, questions, questions? So because circumference is defined using the irrational number pi, it becomes really convenient to use pi or leave your answers in multiples of pi rather than approximating it by some decimal, right? So it just makes a lot more sense that this is angle pi than to say that it's angle 3.14159 and round it to something. Not only is that ugly, it's also inaccurate because you're just rounding. Why not just leave it as its exact answer by just writing pi, and it's just more convenient to write it that way. Good. Questions, questions, questions? Same with, yeah, go ahead.
Those pictures aren't technically correct, are they? Like when I'm looking at the 1 radian, never mind.
No, I get what you're saying. You would think it would be smaller, right? Because you're like 1, because you think of 1 degree. Remember that when we're back in degrees, this is a fantastic question. When we're back with degrees, the whole thing was broken up into 360, right? So there's like these little things like this, and there's like this tiny little thing is 1 degree. And then you go all the way around, and it's broken up into 360 degrees to do 1 full lap. Whereas in radians, it's broken up. It's not broken up between 0 and 360. It's broken up into 6.28. Right. So if we go all the way around this whole thing like this, there's an angle that goes all the way around. It's 6.28. It's not that much. It's not a big number. So
like metric to imperial almost.
Right, exactly. There's just different units, and so you get a different sense of it.
Yeah, okay. That clears it up. Thank you.
Sure. So, this guy right here, instead of saying pi, I could also say 3.14 rads, approximately. But pi just sounds better. It's easier to write it down. It's more accurate since 3.14 is just a really ugly approximation. And I could do pi divided by 2. Oops. Pi divided by 2 gets me to 1.57. So this thing I could say it's 1.57079 radians. Good. I mean, you could confuse someone and say, when you give instructions, instead of saying go up there and make a right turn, okay, that makes sense. So you can go up there and make a pi over 2 degree turn. Okay, they might get that. Or you can tell them go over there and make a 1.57079 radian degree turn. Whoa, what the hell did you say, right? That's just confusing. But they're all the same. They're all equivalent to each other. Initially, you're like, why in the world would we define radians? I mean, degrees make a lot more sense, right? We're used to it, right? When we hear it in our everyday sense, if I go up, if I stop anybody and I tell them go there and make a 90-degree turn, most people know what that means, right? You've grown up with that idea of what 90 degrees would look like. And phrases like, he did a 180-degree turn, right? Like, oh, okay, that means he completely turned around, right? And then there's people that don't understand the actual math and just memorized it wrong and say, he did a 360-degree turn, and you're like, that doesn't mean anything. That means he's going in the same direction. He didn't change his mind. He's doing exactly what he was supposed to be doing. Anyway. So
Did you say he did a 3.14 radian turn?
A 3.14 radian turn, exactly right. He pi radian turned. Oh my God! So, you can throw some math nerdiness at it. So this was 1. Remember, the whole thing is 6.28. So this is a distance of 1, and here's a distance of 2 radians, approximately. And it's intuitively not there, right? Like if I told you approximately how big is 2 radians, it's kind of hard to visualize it until you see it. I mean, I can see right here that it's a little bit bigger than 90 degrees. We can visualize 90 degrees, but it's hard to visualize 2 radians, right? Okay, so I like to go back and forth between the two because this makes more intuitive sense. If I tell you something in degrees, I think it's a little easier to visualize what that means. Is it a big angle? Is it a little angle? Does it do a full rotation and then leave you a little extra? But in terms of radians, it's just kind of hard to visualize what it is. However, the reason we do radians is because it's defined, through a more mathematical way. The math makes a lot more sense. It's easier to work a lot of things. Some of the formulas work out really nicely. Things cancel, reduce, and they work out really nicely. So that's why we like to push this idea of radians. Good, kind of like same as like the metric system, for example. Its definition for things is a little bit more rooted in science. What is a meter? What's a measure of distance? Well, in the metric system, they went out and tried to find something in nature that can be measured and is relatively consistent and has something we can hold on to. What is a second? What is a unit of weight? How do we figure out how much to weigh things by? So I think a meter has something to do with like the circumference of the Earth or the diameter of the Earth. One of the two. They took
One of the kings was doing 2 cobs of corn was equal to roughly.
In the English system?
Yeah, there's a whole documentary on it.
Yeah, it's fantastic. I mean, the English system is just nuts. Absolutely nuts. Like, let's just take the king's thumb and we'll use, that's an inch. That's the king's thumb. I don't know, just weird, random things like that. Yeah, they grab the rock. I don't know what rock, some random rock. I'm like, here, this is what a unit of weight is. Put that rock on there. Everyone knows that rock. It's just weird. But the metric system's a little bit more consistent. So, but we're used to it, right? In our part of the world, we're used to it. We have a good sense of what what feet are. I'm 5'10" tall. You kind of have a sense of how tall that is because we're used to that. But if I told you I'm 6.25 meters. Oh, I'm really not 6.52 meters, but something is 6.52 meters tall, it's kind of hard to visualize what that is, right? But it's just a unit of measurement that we're just used to. You can easily convert it to something else, like cans of Coke. how many cans of Coke tall are you, right? I'm 17 and a half cans of Coke tall. If the whole world adopted that, then we would all be used to that as a measure of distance, right? The height of a can of Coke, an aluminum can Coke. Anyway, so going back to this thing here. So we're used to this. So I'll often go back to degrees so that we can kind of visualize things. They're more intuitive. But we do need to push ahead and really work with radians because the formulas work out really nicely. And, initially, all the formulas we work with are easy to derive, and we can just kind of do them ourselves. But eventually we get to a point where the formulas presented are really difficult to understand where they come from and how they were developed. And it's important to realize that almost all of them assume that you're working with radians, so that the formula only works when you plug in a radian. Right? The input says plug in an angle, and then this, that, and the other will pop out the area of a triangle or the area of some shape. But most of those assume that we're working with radians. Good. Okay, the relationship between radians and degrees. Here it is. We said that one full turn of this thing here is 360 degrees. And one full turn of this thing is 2 pi. So we can say that these two things are equal to each other. So this is the connection between the two. Or, okay, well, we can just go halfway. Halfway in this direction, well, that's just going to be 180 degrees. And halfway between this in radians, halfway, well, that's just going to be pi. So we can use that relationship between the two, or that relationship between the two, either one. This one's easier to memorize since we're all intuitively aware of 360 degrees is a full turn, and 2 pi seems like a pretty easy thing to do. So in terms of just memorizing it, I think this is the better relationship. But then that can easily be reduced into this relationship, which is the most common way that people relate it. Okay, so 180 degrees is equal to pi radians, just the way 360 degrees is equal to 2 pi radians. Good. So we can use this as a way of converting between radians and degrees, and the other way around. Good. And we're going to use that relationship right there. So when you're asked to convert something, I'm sure that's the next thing down here, some examples of how to convert. Just keep track of the units. Like if you want to go from 60 minutes equals, well, minutes equals 1 hour. Right, we have that relationship. So if you want to convert 3.25 hours to minutes, then 2 minutes to 2 minutes. How many minutes is that? We use this little thing here, so it's going to be 3.25 hours. Put it as a fraction times, and then think about the units, how they cancel. I want the hours to cancel down here, and then I want my result to be in terms of minutes. So now here I know that there are 60 minutes in 1 hour. Good. So now the hours will cancel, and I know that if I multiply this times this, my answer will be in minutes. Good. And the other way around, if I wanted to know how much is 485 minutes in terms of hours, okay, so now again, 2 hours. Then keeping track again of the units, minutes, turn it into a fraction, times, and then we're going to put minutes down here, hours up here, and now there are 60 minutes in 1 hour. The minutes cancel, giving me hours. So it's this number, 485 divided by 60, that'll tell me how many hours that is. So in the same spirit, we're going to do the same thing here. Keep track of whether we're starting with degrees or whether we're starting with radians. Turn it into a fraction, cancel the units out, and then use this relationship to either multiply by this fraction here or this fraction here to get to your result. For example, express 60 degrees in radians. Okay, so, so for part A here, we have 60 degrees times, right, and I want degrees, so degrees, to cancel out with those degrees, and my output to be radians, so I know that it's got to be in this order, right? And then I look at my relationship, and I know that there are 180 degrees in pi radians, that these two are equal to each other, right? Because they're equal to each other, that means that this whole fraction here is just equivalent to 1, right? So we're multiplying by a new version of 1, we're not really changing the value, but I know that the degrees will cancel with that, and my output would be in radians. Good. So it's just going to be the multiplication of these two, so it's going to be equal to 60 pi over 180, and now we're in radians, rads. And then we can reduce. 60 goes into 180 3 times, so this is just pi over 3 radians. Good. But again, we get back to this issue of it not being intuitive for most people until you do this for a while. But you know, a 60-degree angle, we kind of have a pretty good sense of what that looks like, how big it is. But pi over 3 radians, it's not as intuitive until you spend some time with it. Okay. For part B, we want to start with radians, so we have this pi over 6 rads, right? Turn it into a fraction over 1. We're going to multiply this by another fraction, and I want rads down here to cancel, and then I want this to go over to degrees, and then the relationship is 180 degrees over pi radians. Good. Okay, so we end up with these rads cancel, and we just end up with pi over 6 times 180 over pi degrees. And so the pi's cancel. 6 goes into 180 30 times. And so we get 30 degrees. Easy, right? Any questions? Okay. So that was the solution. That's what the author did. Same thing. Looks good. A note on terminology. We often use a phrase such as a 30-degree angle to mean an angle whose measure is 30 degrees. Okay. Also for an angle 30 degrees, pi over 6 measure. Okay, same thing. If no unit is given, this is important. When no unit is given, by default we assume that it's measured in radians. Okay, so keep that in mind. All right, more definitions. Angles in standard position. What is standard position? Remember that before, when we just defined what an angle was, it could be, you know, this could be an angle like that. And so we had this theta here, and then we had ray 1 and ray 2. We have something called the initial side. And then the other one is either called the working side or also called the terminal side. I'm not sure what they called it here, I forgot. Let's call it the terminal side. Okay, so the initial side stays fixed while we get to move around the terminal side, right? So this guy's the guy that slides back and forth so that we can create different angles. Good, so this thing stays still. Okay, so now if we grab any random angle and we move it around and we station it on a rectangular coordinate system in this way, Or, I mean, you can either think of moving the actual angle, or you can think of creating the axes on it, right? So we could say, okay, well, here's the angle given in this weird thing. Why not define the x-axis to be this? And then we can create the y-axis to go in this direction. And there, we've done exactly what we wanted, right? So you can either think of moving the angle into this sort of a position where the initial side is on the x-axis and the crosshair point is on the origin of the rectangular coordinate system. Good. The vertex of the angle on the origin. Good, good. All right, well, when it's in this position on our rectangular grid, then we call that standard position for our angles. Right? An angle is in standard position if it is drawn in an xy plane with its vertex at the origin and initial side on the positive x-axis. Fairly easy, right? Chapter 6, pretty easy. Okay, good, good, good. Any questions, any questions, any questions? No? So here's just lots of examples of what an angle in standard position could look like. Right? So in every single case, the initial side of the angle is over here on the x-axis. So here's an angle that ends up being in quadrant 1. Here is an angle that goes in this direction and ends up in quadrant 2. Right? So the initial side is over here, so it's this angle down here. Right? Here is an angle that does a complete rotation around our grid. So in degrees, it would go past 360 degrees, a little bit more than that, and ends up in quadrant 1. Okay, moving on. Two angles in standard position are coterminal if their sides coincide, right? So if the initial side, well, for all angles in standard position, the initial side is the x-axis. But now if the terminal side, or the working side, the other side that's moving, if both of them end in the exact same position, then we say that they're both coterminal angles. Okay, so for example, find angles that are coterminals to 30 degrees in standard position. So that's fairly easy. Let's draw some sketches here. So here we have the y-axis, the x-axis, and we know that 30 degrees is going to be somewhere around here. So let's say that this guy right here is 30 degrees. Okay, so here is an angle in this side that is 30 degrees. Okay, well, another angle that does the same thing, like let's say maybe I start here and I go all the way around, and I come back and I end up there in the exact same place. So let's dot it now. Well, this angle that goes all the way around and ends up in the same place, that's going to end up giving me another coterminal angle. So one full rotation was 360. Like up to here, we had gone 360 degrees up to here. And then a little extra to get to the 30 degrees into quadrant 1 would make it 390 degree angle. Good. So we would say that 30 degrees, and 390 degrees are coterminal. Coterminal. Yes?
Why does it always go counterclockwise?
It's just an arbitrary choice that somebody made, right? Again, I think we give credit to the Babylonian Empire for thinking of it this way. I don't know. Why does it? Why are there 12 hours in one day? I don't know. Just kind of arbitrarily chosen, right? Why do we have 12 months? Who knows? 12 months is more of a religious thing, right? Because Jesus, that's why we have 12 months. But, you know, why not 10 months? Why not 20 months, right? So it's just, there's some things that are mathematical and there's like a really good reason, like pi. Pi is not a man-made thing. It's just we discovered that that's the way it works for a circumference. But you know, for
No, I was just making sure that I like.
oh, gotcha. Yeah, I know. I like to go on my own little rants. Appreciate it.
No, you're good.
So yeah, it's always this way is positive, and let's come up with some negatives, right? So if your angle starts off on the initial side and you go in this direction, you know, it's traveling in this direction, this direction, this direction. This is always positive for angles. Positive direction is always this way, counterclockwise. I don't know why they chose it to be that way. We can try and fix it now, but then, you know, how do we get the whole world to agree that the other way should be positive? I don't know. Okay, so then let's find a coterminal that goes in the other direction. All right, so let's find one that starts off here, and then I don't know how messy this is getting, but let's say we start off, the initial angle is here, and I want to go in the opposite direction, so I want to go this way and end up there. Well, that's an ugly turn. Go here and end up over here in the opposite direction. So I know that this is going to go in the negatives. So as I go this way and I end up there, I don't quite make a full rotation. If I went all the way around, it would be negative 360. And I want to stop a little before that. So I need to go negative 330. Good. So I can just tack that on to the list here. Negative 330 degrees, 30 degrees, and 390 degrees are all coterminal. Right? No matter how you describe it, they all end up describing this angle that goes right in there like this. Right? Well, they don't describe that angle. They end up describing this angle that has this sort of that opens up this much. Like, how do we describe this? Well, we can describe it by any one of these angle thetas. Okay? So, if you notice the pattern then, to get from this one to the next one, I did one full rotation and then added a little extra. So, to get a coterminal angle, you can always just add multiples of 360 or subtract multiples of 360. Good. So, 300 and, so this is for part A still, 30 degrees, and then if we add or subtract multiples of 360, n, where n equals any integer, so like negative 2, negative 1, 0, 1, 2, 3, dot, 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 that way, dot, 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 this way. This describes all coterminal angles. Good? Good, good, good. So you can create a table and have all the answers right here, all coterminal angles of 30 degrees. So when n is equal to 0, we end up with 30 plus or minus 360 degrees times 0, which just gives us 30 degrees. When n is 1, we end up with 30 plus or minus 360 degrees times 1, and then this leads to 30 plus 360, which gives us the 390, or the 30 minus 360, which gives us the negative 330. Good. And then when n is 2, we end up with 30 plus or minus 360 times 2, which again gives us two answers. 30 plus 360, or let's say 720. 30 plus 720, which gets us to 750 degrees. These are all in degrees. And then 30 minus 720, which gets us to negative 690. Right, so this little formula can just generate all of them, adding and subtracting multiples of 360 degrees. Having that as a clue, right, it was kind of intuitive to think about where is 30 degrees and how do we add a full rotation. But armed with that idea that it's just adding and subtracting rotations in degrees, we can do the same thing for the radians now. Find the coterminal angles of pi over 3. For part B, then I can just say that it's got to be pi over 3 plus or minus full rotations in radians are going to be pi times n. Good. Where if n is 0, then it's just pi over 3. But when n is 1, we can end up with pi over 3 plus 2 pi. That'll give us one coterminal angle. We need a common denominator, which is going to be a 3. So let's go ahead and add this. 3 over 3, which gives us 6. That makes it 7 pi over 3. 7 pi over 3. Good. Questions, 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 questions? Or we can do pi over 3 minus 2 pi. Again, multiplying it by 3 over 3. 3 over 3. And we end up with pi minus 6, which makes it negative 5 pi over 3. Right, so again, degrees are just more intuitive for us. We're comfortable thinking about what is negative 330 degrees, what's positive 750 degrees, but I think it becomes a little bit more difficult to visualize what 7 pi over 3 is, or what negative 5 pi over 3 is. Questions, questions, questions? Good. So we can just keep going and do more of these if we wanted to. It doesn't matter. Pi over 3 plus, say, 2 copies of pi over 2. That'll give us another coterminal angle. Again, I'm going to need a common denominator every time, so I'm going to have to put a 3 there and a 3 there. So that would be 4 times 3 makes it 12, plus 1 makes it 13. So 13 pi over 3 is another coterminal angle. Good? So we have that pi over 3. Come on. Man. So we have that pi over 3 and 7 pi over 3 and negative 5 pi over 3 and 13 pi over 3 are all coterminal angles. Don't confuse them with reference angles, which I know you've all had trigonometry, so you've worked with reference angles. They'll be defined shortly. We'll get to reference angles, but these are coterminal angles. These are not reference angles. Any questions? No? So two angles are coterminal if when you draw them, they look identical. You can't even tell anything has, been different. They both result in the same angle being drawn, and they're both coterminal angles. Good, 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 good. Let's see. Yep, same thing we did. We found the same coterminal angles. They have nicer graphs for them. So here's 30 degrees. And then if you go all the way around, that's 360 degrees plus an additional little extra guy here, which makes it all the way to 390 degrees. Or you can go in the other direction. So here are 3 separate coterminal angles. No matter which angle you're working with, at the end of the day, you just end up with this blue ray here and the initial side. So you get the same angle. They draw the same picture. Different angles that draw the same picture. Good. Same thing with the radians. You get to add multiples of pi's. So this is the same ones we came up with, I think. And then some better pictures. Pi over 3 looks like this. And then if we go all the way around one time, we end up with 7 pi over 3. We can also go in the other direction and come up with negative 5 pi over 3. You can add another multiple after that and get negative 11 pi over 3. Fairly easy, right? Questions, 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 questions? Questions, questions, questions? No? Okay, lengths of a circular arc. All right, so radians are defined on the unit circle, right? On the unit circle, we have big circle, we have the radius goes out this way in any direction, and we have r equals to 1, so that when we have an angle, that's supposed to be a circle, sorry about that. So when we have an angle theta, we defined what theta is in radians. We defined it to be this distance over here, whatever that is, whatever that section is. We defined that length there to be the theta in radians. Okay, but what if we're not on the unit circle? What if we're just on any random circle? Right, so this is the unit circle for sure, but what if we just have some other random circle that's not necessarily the unit circle? Okay, well then, let's see what that is. We have some value r there, and then we still have some angle theta there. And so then we want to define what theta is. Right, we have s there, so it's not necessarily 1. So how do we define it? So the way we define it is to think about it as a percentage of the whole thing. I hope that makes sense. Okay, so the entire circumference around the whole thing. Remember the formula for the circumference of the circle. Circumference of circle is equal to 2 pi r. Right? That's the formula for the whole thing. Okay. So what we want to say is that whatever percentage this is, a percentage, it's going to be the same percentage of the entire thing. So in degrees, let's say that let's say we wanted to define what this is. What do I want to do? Let's just start with a really easy one. Like if we had just that right there, right? I know this should be 1/4, right? This is 90 degrees. It should be 1/4. So this guy right here, theta, it should be the case, right, that I want to be able to say that theta over 360 degrees, the whole rotation is 360 degrees. So this ratio should be the same as, or when we multiply that ratio times the circumference of the entire thing, it should give us this distance over here. This distance here, s, should be equal to, and I don't know why I have it in red, but I have lots of colors going on now. Should be equal to this times the circumference of the whole thing, 2 pi r. I don't know if that seems reasonable. It should be reasonable from this, that s equals to 1/4 of the circumference. That's what I'm trying to say. And computer doesn't like that. Circle. Does that make sense, what I'm trying to say here? If in this case, this thing is equal to 90 degrees, so if this is equal to 90 degrees, it's 1/4 of the entire rotation. So therefore, this s distance should be 1/4 of the entire circumference. So the s should be 1/4 of the circumference of the circle. So s should be equal to 1/4 times pi r squared. Sorry, pi r. Good. Kind of, maybe, sort of, kind of, maybe, sort of. Good. Okay, so so in general, then this should be that s should be equal to theta over the 360 degrees times the pi r squared, the circumference of the circle, right, times circumference of circle. So that's a fairly good formula, except that it's when it's in degrees, it doesn't quite work out as nicely as it does when you think about it in radians. If we think about it in radians instead of degrees, then things work out really nicely. So instead, if we think that this is equal to theta over, and remember the whole rotation all the way around is 2 pi, and now the circumference of the circle is 2 pi r, and then look at those 2 pi's cancel. 2 pi and 2 pi cancels, and so we end up with s equals to theta r. And that's this formula right here. This formula given comes from this. Any questions? I don't know if I did a very good job of this. No, sort of, kind of, maybe. Okay, so this formula comes from this. It's a ratio of the entire circumference, and when you do it in radians, then units cancel really nicely, and you end up with a really nice formula. So the distance s around the circumference of the circle, a distance s subtended by a particular central angle, central angle theta in radians, is equal to the angle times the r value, where r is the radius of the circle. Yes? Questions? No? No? We're good? From here, we can easily solve for theta by dividing both sides by r, and we get that s over r equals to theta. So we can solve for any one of these three variables, and this one's just a useful formula we use. Questions? Okay, so this formula allows us to define radian measures using a circle of any radius r, not just the unit circle. So the radian measure of an angle theta is s over r, where s is the length of the circle arc that subtends theta in the circle of radius r. Good, so we're able to extend beyond the unit circle because of this relationship. So find the length of an arc of circle radius 10 meters and subtends the central angle 30 degrees. Okay, so here we have some sort of a circle, and we have if the radius is 10, it doesn't have to be this way, but okay, so the radius is 10 meters, and we have an angle of 30 degrees. So we go up there, and this is 30 degrees. And the question is to figure out the length of the arc, right? So we want to know this length over here, s, right? So what I was attempting to describe is the following, that the value s, and I don't know if I did a very good job up there, but let's try it again. The value s should be a percentage of the entire thing, right? The entire circumference all the way around is equal to pi r squared, right? So the entire circumference from there all the way around here, the circumference, well, that looks weird because that looks like just another big circle, huh? So from there, coming all the way around to there is the circumference of the circle, which is equal to 2 pi r, which in our case is just 2 pi times 10. Or 20 pi. Good? Okay, so now S is a portion of that. It's a ratio of that. Like, if it was 90 degrees, it would be 1/4 of that. If S went all the way over here, it would be half of that, right? But it is 30% of that. So what we want to say is that S is equal to 30 divided by 360 times the circumference of the circle. Good. Any questions about that little relationship? So S equals 2. So we can reduce that. 30 goes into 360 12 times, right? 300. Yeah, so this is just equal to 1/12. This turns into 1/12. And then the circumference of the circle we said was equal to 20 pi. So it makes sense that S is 1/12 of 20 pi. Right? We multiply them together, we reduce, they both have a common divisor of 4. So this becomes 5 pi over 3. S equals to 5 pi over 3. S equals to 5 pi over 3. Good. Questions? No? Okay, so I did that again the hard way of kind of visualizing what this is and putting it into my formula. The other thing I could do is, first of all, turn it into radians, because our formulas work best with radians, so we'll see why. So let's first of all think of what that is. So we have a unit circle, not the unit circle, sorry, we have a circle, and we have this as 10 meters. So then we know that the entire circumference is exactly the same, so same circumference for this circle. But now I want to think about what 30 degrees is in terms of radians. So we want this right here in terms of radians. And we know that to do that, we multiply 30 degrees times a fraction where we have degrees down here and radians up here. So it's got to be 180 degrees and then pi over there. And then this reduces, right? This cancels with the degrees. 30 goes into 106. 30 degrees goes into 180 degrees 6 times. So this becomes pi over 6 radians. So we have pi over 6 here. Pi over 6. Good. All right. So now again, we want to find out this value here, this value S. And just like before, we set up this little formula where S is equal to a ratio. S equals to whatever this angle is divided by the entire thing. So it's this pi over 6 out of 2 pi times the formula for the circumference of the circle, which is equal to 2 pi r. 2 pi r. Good. And the reason we leave it this way, or the nice benefit of this, is that the pi's cancel. 2 pi cancels with 2 pi. Right here, this 2 pi was being used because it was a ratio of the whole thing, right? This angle, pi over 6, then the entire divided by the entire thing, gives you like a ratio, a proportion of how much this angle is relative to one full rotation, just like 30 over 360. And then the formula for the circumference of the entire circle is 2 pi r. The 2 pi's cancel, and I'm left with s times s equals pi over 6 times r. Times r. Pi over 6 times r, which is equal to the angle theta, right? That's where this formula comes from. It's just equal to s equals to theta times r. Right, theta in radians. So point is, we can save ourselves a lot of work here and just deal with the formula without having to kind of think our way through it. The formula is just theta over r. Good. So all of this work is not required when we want to solve this. If we know our formula, let's just go back over here and see what, if you look in the back of the book and find the solution, the author would probably just jump to say that the length s is equal to theta times r, where theta is in radians. So you'd still have to do that work over there to figure out what theta is in radians, right? So then theta is going to be equal to 30 degrees times pi over 180. So we still get the pi over 6 radians. So then we stick pi over 6 into here times 10, and that's s. So s, now we just reduce. 2 goes into here 3 times, 2 goes into there 5 times, so then that's how we get 5 pi over 3. Same answer as before. Any questions for part A? No? Okay, so for part B, we can just use the formula. Central angle theta of a circle of radius 4 is subtended by an arc of length 6 meters. Okay, so for part B, we have some sort of a circle. It's supposed to be a circle there, sorry about that. We have a central angle theta. So I don't know, we have something like this. Here is theta. We know that the radius is 4 meters. R equals to 4 meters. And we know that the arc that it subtends, usually denoted by S, so this little section right there, S, is equal to 6 meters. Good. And so now they want us to find the central angle theta. So from the formula of S equals to theta R, we divide both sides by r, and we get that theta equals to s divided by r. So from that, we can easily conclude that theta must be equal to 6 divided by 4 radians. Remember that this formula is in radians. In radians. So it's equal to 6 over 4 radians. We can reduce that and say that theta equals to 3 over 2. So the answer is going to be theta equals to 3 over 2 radians. Good. Questions? That reduces to 1.5, so we can also say 1.5 radians. Or theta equals 1.5 rads. Any questions? No? We're good? No questions? Okay, so using the formula, we can convert 30 degrees into pi over 6 radians. plug it into our formula. We get the same answer. For b, same thing, 3 over 2 radians or 1.5 radians. Area of a circular section. We're going to do the same thing as before, kind of reason our way through it real quick. So in degrees, if we have a pizza, here's our big pizza, and we want to find the area of a slice, right? We want to find this area. What is that area? Given that we know r and we know theta, some angle theta in there. Okay, so what we want to do is think about the area of an entire circle. Remember that the area of a circle is pi r squared. And so now this slice here, this slice is going to be a percentage of that entire area. Like if the slice was half of the thing, right? If this was my slice, then I would say that the area of that slice, is equal to 50% of the entire thing. And the entire thing is pi r squared. Right? 50%, well, I can also say it's 1/2 times the entire thing. Good. Or if the area was another simple one, like maybe it went down here, and here's this whole thing. What if I ate all of this? Right? This whole thing was my slice. That area there that I shaded is 3/4. That's another easy one. So this is my slice, my area of this slice. Area of slice is equal to 3/4 or 75%. 75%. Well, that was weird. Hummingbirds just ran into my glass. Anyway, 75% of the whole area, so it would be 75% of pi r squared. So here we multiply this by pi r squared. Right, so it's the area of the entire circle, and then we multiply it by some ratio that describes that angle theta. Good? Okay, so hopefully then it's intuitive that if we have this in general, let me redraw it over here again. So then if we have the entire thing in general, and we want to know what is the area of this slice, that's an ugly slice. We have some angle theta, and then we have some value r, and we want to find the area of this slice, we call a sector, capital A, equals area of sector, slice, area of the sector, so A is going to be equal to theta over 360 degrees, and that'll give you the proportion, the ratio of the entire pizza, right? So if theta is 90 degrees, that'll be 1/4. 90 over 360 is 1/4 of the entire area of the entire thing, right? So times area of entire circle. Good. Okay, but it's not going to work out very nicely. This works, it's true, but again, it works out nicer if we think of it in radians. Right? So I'll just put or the area equals to theta over 2 pi in radians. Right? So here theta was in degrees, but now we're going to go over to radians. And then same thing, this will give you a ratio, a proportion of area of the entire circle. So A is going to be equal to theta over 2 pi times the area of the entire thing was pi r squared. So now the pi's cancel. and we're left with a equals to 1/2 theta r squared, which is where they get this formula from. Right? That's what this is. So again, this is assuming that the theta is in radians, because that's how we can get this to cancel. If theta is in degrees, then this is the formula. And it's not that bad, really. It's not terrible, but this is usually the way we work with it. Does that make sense? Any questions? In radians. Right? Otherwise, the formula would be A equals to theta over 360 degrees times 2 pi r. And nothing cancels. Well, I guess you can cancel out this 2 and this 360. So you could also say area equals to theta over 180 degrees times pi r. That looks pretty ugly. And then this would be in degrees. In degrees. Any questions? No? No? Okay, so that's the formula for the area of a sector, a slice of pizza, the area of the slice. And it's the same concept as before. It's a proportion of the entire thing. Before we're looking at the proportion of the entire circumference. Here it's the proportion of an area. Okay, so find the area of a sector of a circle with central angle 60 degrees if the radius of the circle is 3 meters. Okay, so we have a circle and we have an angle of 60 degrees. And we know that this is 3 meters, right? So intuitively, again, we know that, I won't use the, first though, let me just kind of intuitively find it and then we can use the formula for it. Okay, so 60 degrees, if we divide that by 360 degrees, that goes into it 6 times. This is equal to 1/6, right? This slice is 1/6 of the whole thing. That's what I'm referencing here. So now the area A is going to be equal to 1/6 of the entire thing. And the entire thing, the area of the entire pizza is pi times r squared. And r is 3 squared. So that would be that A equals to 9 pi over 6, which reduces. 3 goes into there, 3 and 2, 3 pi over 2. That's my answer. Good. 60 over 360 is a ratio, 1/6. This slice should be 1/6. Area of slice is 1/6. 1/6 the area of the entire circle. And so this is the area of the entire circle right here. This is pi r squared, area of the entire circle. Questions, questions, questions? Okay, so I just kind of intuitively figured out what that was. But, you know, of course we have a nice little formula, so why not use the little formula? So if we wanted to use the formula we discovered is right here. This is the formula for the area of a sector where theta is in radians. So let's just blindly apply the formula and see that we get the same answer anyway. Okay, so I'll put a big or using that the area equals to 1/2 theta r squared, where theta must be in radians. Then the first thing we have to do is convert theta, which was equal to 60 degrees, into radians. So we multiply it by degrees down here to cancel with the degrees there, and radians there. So we have to put 180 there and theta there. This turns into pi over 3. 60 goes into 183 times radians. So there, I have that guy, I know that guy, I can just blindly plug it into my formula, and that will be my answer. A equals to 1/2 times theta, which is pi over 3, times r, which was 3 squared. This, before I square it, I can also cancel this one with one of those, so I'll end up with 3 pi, so I get 3 pi over 2. Area equals to 3 pi over 2. Same as before. Questions, 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 questions? No? No? We're good? Good, good, good? So that's what the author did. Just kind of blindly plugged it into our formula. Converted 60 degrees into pi over 3 radians. Blindly plug it into this little formula, and there you go. You get the same answer. Almost done with this section. Circular motion. Okay, so we got two different things going on when we're looking at circular motion. You got the speed of the angle, angular motion, and then you got the speed at which an object traveling around the circumference of the circle would be traveling. So the equivalent distance traveled along that on a straight line. So if we kind of take a measurement angle, we get the distance traveled is s. S divided by time would give you a speed of how fast this is traveling. Whereas the theta, how fast the angle theta is traveling, is changing, would be measured as theta over time. Good? So we got angular speed, denoted by this little W symbol here. And then that's equal to theta over time. How much theta has changed over a period of time t that has elapsed. Good. So, of course, carnival rides are, for example, heavily dependent on that. So if we think of a carnival ride where it just goes in circles, then if we have, from an aerial perspective looking down, there might be like, a little thing here, I don't know, like a carousel. It could be like a little horse, or it could be, I don't know, some sort of little container that has people in here. And then this thing extends out to it. So here's a little stick people hanging out there. So they're traveling along this direction. So if we look at theta, right, the angle theta is traveling in this direction. Here's theta. So the speed at which theta changes is not bad. I'm sorry, it's constant. We can have some constant speed there. But if the carnival had two choices, maybe this thing extends out and you can sit here, or there's another place over here where you can sit over here. We had two choices so that this thing keeps changing that way. Then as theta changed from this point to that point, say in 4 seconds, in 4 seconds, theta changed this much by this angle. That would be angular speed. Both this person and this person would be experiencing the exact same angular speed because 4 seconds later, they will have traveled by this angle, right? 4 seconds later, this thing's over here, and this person is now here, and this person is now over here. So they've both experienced the same angular speed. But if we look at the actual distance traveled, this person traveled along the circumference of this circle here. They traveled this distance here. They traveled this distance in 4 seconds. So this is their linear speed, right? whereas this person traveled this segment of a much larger circle. They traveled farther in the same time. So it would make sense that this person is going faster, right? If you travel a bigger distance in the same 4 seconds, then you're traveling faster, right? So this person feels like they're going much faster than this person, right? The closer you get to the center, the slower it feels, linear speed-wise, and the farther out you get, the faster it feels, linear speed-wise. Good? Questions? Sort of?
That's like the same concept of putting taller wheels on the car to reach a higher top speed.
Good point. Yes, exactly. So if we have a car, the circumference of the wheels make a big difference for certain things, right? So if we have, this is my most awesome drawing of a car. Oops, well, whatever, go like that. So if we have tiny little wheels, then, from the perspective of the engine rotating that, then you got to make one full turn in order to travel the distance which is equivalent to the circumference of the wheel. On the other hand, if we put really big tires on it, then the engine is still just making one rotation, but in one rotation you will have traveled the distance which is the circumference of the tires, right? So one rotation will get you farther in the green wheels than one rotation will get you in the red wheels. However, then you have to take into consideration how difficult is it to turn one rotation, when the torque needed to turn this green wheel versus the red one. But something very interesting about these tires is that when a car turns, and now this is kind of like an aerial shot of this same truck, and forgive my drawing, but this is supposed to be an aerial shot of this truck. What's that?
Are you talking about the inner wheel turns left?
Exactly right. From an aerial shot, if this truck was turning, then the inner wheel would be traveling, this much distance, and then the outer wheel would be turning this much distance. So it has to travel farther than the inside wheel, right? So early on in the development of vehicles, both tires were kind of locked together, so that when the car turned, all of a sudden we have a problem because this one is going at the same speed as that one, and then, like we said, the outside one has to go farther. So it ended up causing a lot of accidents. It was a very dangerous time to be driving those cars. Until somebody invented a way to cause the inner wheel to rotate less than the outer wheel, so the outer wheel rotates faster as it's turning. It automatically does that, so that they travel the same distance in the same. I'm sorry, that this one travels the larger distance in the same time as this one travels the shorter distance.
Yeah, they were able to unlock.
Right. What is that called? Is that called the differential? I want to say, is that the differential? Okay.
Yeah, there's a lot of slang terms, but
okay.
Will we be getting into like surface speed or surface
speed? What do you mean by surface speed?
Well, I guess that answers my question.
Probably not. So this is just basics here. We got angular speed, we got linear speed, and we're going to be looking at this other formula it's down here for the relationship between the two, which is the connection between the angular speed and the linear speed.
Okay.
What is the surface speed?
Well, so if you're looking at the red wheels, it's turning. Like, if you're looking at the red wheel and you're looking at spin, the actual face, or like the outer part of the red wheel is turning slower. But if you're looking at the green, like face of the wheel, like the outer part, it's turning a lot faster because it's a lot bigger. So it's like if they're rotating like, let's say 20 RPMs, it's hard to like explain, but it's like
Okay.
the face of the red.
So you're back to this idea of comparing little wheels versus larger wheels.
Yeah,
Okay.
Like the only reason why I know about this is like, you know what a loop is? It's like certain. What not? No.
Okay.
Sorry.
There's a lot of interesting things there. I don't know if any of you guys are planning on going into like designing, like automotive engineering kind of stuff. Lots of good jobs there moving in the future, right? We're electrifying everything, and the choice of tires makes a big difference with the efficiency of the vehicle. So that's why it's kind of a big deal to pick the perfect tire. And I think we kind of mathematically prefer a smaller wheel for it to be more efficient. It probably varies by speed and the type of car and all that. But I don't believe I don't believe the math favors larger wheels for efficiency. But we just like larger wheels. They look cool, and larger wheels are efficient for certain things like off-road driving and stuff like that. But there's this battle between the two, and then soon we're going to get into the types of tires that don't have an inner tube. I think that's where we're heading with tires. I don't know if you've seen any of those. They look pretty cool. They look cool and they last longer, and they don't puncture because there's no inner tube. So my guess is that we're heading that way. Any rate, moving on then. Let's look at an application of these, right? So we have angular speed, right? That's the angle. The angle traveled, the change in the theta divided by a unit of time, and then the linear speed, which is the distance traveled, s, along the arc divided by t. Long string at a rate of 15 revolutions every 10 seconds. Find the angular and the linear speed of the stones. Good. So, for all intents and purposes, we have a giant circle where the kid is in the center of the circle, and we have some sort of string that has a radius of, 3 feet. 3 feet. And then there's a stone at the end, and he starts rotating this way, and he rotates it, theta. Theta is given by 15 revolutions per 10 seconds. So theta is equal to 15, not theta, omega. So we're given, rotates, find the angular, okay, so the angular speed, is equal to W equals to theta over time elapsed. So we have rotates 15 revolutions every 10 seconds. So 15 revolutions is 15 laps all the way around. So that would be 15 over. Wait, I don't know if they want to use. Let me see what I want to match up what the author did here. Yeah, they stuck with it in radians. Okay. So 15 times 2 pi, right, over a 10-second period gives us 30 pi over 10. Okay. So then W equals 2. This reduces to 3 pi, and this is radians per rads per second. W equals to 3 pi rads per second. Good. And that matches what they did, rads per second. Good. And then our other formula, v for the linear distance, is equal to s divided by t. Okay, s divided by t. And so we know that if we want to figure out the actual distance traveled, we need to think about this. And we know that s is equal to r times theta in radians. In rads. So v equals to, so then v equals to s over t is going to be that it's the same thing as r theta over t. Where r is the radius, that's just going to be a fixed value of 3, and then theta in radians, we need to figure out what that theta in radians is, which is equal to this. So it's going to be equal to 3 from the radians times 15 times 2 pi. But okay, t is 10 seconds. And the distance traveled in those 10 seconds is given by this formula, right? We already saw that before. R theta is the distance of the arc. So we get this little product. Okay, anyway. And then this reduces a little bit. The 2 goes into the 10 5 times. So then we do get a little bit of a reduction. 5 times. And then the 5 goes into the 15 3 times. So we should end up with 9 pi. Still feel like I did something wrong. How do you get a 90 pi? Oh, no, that's not the travel that. So the answer is 9 pi feet per second. Okay. 9 pi feet per second. Right, this is in feet. Feet per second. Let's just look at the author's work here. So the distance traveled in 10 seconds is s equals to 15 times 2 pi r, where this is our formula for s. And so it traveled 90 pi feet, and in 10 seconds we get 9 pi feet per second. Okay, any questions about that? No, we're almost done. The relationship between the two, as we just showed, the relationship between the two is connected by these two things. We have that this is equal to theta over t, and we have that v is equal to s over t, but we also know that s equals to r theta. So if I replace the s with an r theta, and then theta over t, just kind of group it up that way, and so we get that this is equal to r w. Right, so that's how we get the connection that v equals to rw. And that's where they get this formula here. A point moves along a circle radius r with angular speed w, then its linear speed v is given by r times w. Good. So a woman is riding a bicycle whose wheels are 26 inches in diameter. So we have the radius r in inches. If the wheel rotates at 125 revolutions per minute, find the speed in miles per hour at which she is traveling. So to visualize this, we have a circle, and we have this thing over here from there to there, and this is the diameter is 26 inches. So that's the radius. The radius equals to 26 inches. If the wheels are rotating at 25 revolutions per minute, so that's going to be angular velocity is equal to 125 revolutions per 1 minute. Turning 125 revolutions into radians, right? 1 revolution is 2 pi, so it's got to be 125 times 2 pi's over 1 minute. Right? So its speed w is equal to 250 radians per minute, 250 pi rads per minute. Good. Questions. And so we know that, what do they want? Find the revolutions per minute, find the speed in miles per hour at which she is traveling. Okay, so then in terms of inches, so then her speed v is equal to this times r, radius. I'll just put that here. So v equals to w times r, and we already found w. So v equals to 250 pi radians per minute. And we want to multiply that by r, which is 26 inches. And that'll give us an answer in inches per minute. But we want to be able to convert this into miles per hour. So we need to use conversion factors. So there are 12 inches in 1 foot, and there are 5,280 feet in 1 mile. And then time-wise, there are 60 minutes in 1 hour. Good. So the velocity we are seeking is going to be this 250 pi, and it's going to be rads per minute times 26 inches times, and then I want to cancel out inches and go from inches to feet. I'm going to run out of space here. Inches to feet, and then from feet I want to go to miles, from feet to miles, and then I want to go from minutes, and I'm going to put minutes up here so that they cancel out with those minutes, and then hours over here. So just looking at the units, minutes will cancel with minutes, and inches will cancel with inches, feet will cancel with feet. And so I'll end up with the only thing that survives, it's going to be miles over hours. Right? So it'll be in terms of miles per hour. Good. So now we insert all our conversion factors. So there are 12 inches in 1 foot. There are 5,280 feet in 1 mile, and there are 60 minutes in 1 hour. So at the end of this whole thing, we see that we need to multiply 250 times pi times 26 times 60. The whole thing gets divided by 12 times 5280, and that should give us our answer. Did I mess up somewhere?
Correct me if I'm wrong, but did they say the diameter is 26 inches?
Oh man, did they? They did not?
Yeah.
26 inches.
So wouldn't you cut that in half if you're going for the radius?
You're absolutely right. So, riding a bicycle whose wheels are 26 inches in diameter, not in radius. Okay, absolutely right. So this is, the radius is 13 inches then, not 26. The diameter was 26 inches. So then that converts things, that hurts things over here, so that stays the same. So that just changes this thing here, so this should be 13 inches. And that gives us 13 inches there, which means that there should be 13 inches there. Good. Let's see what the author did for this thing. Okay, so 2 pi times 125 gets you to 250 pi radians per minute. Since the wheels have a radius of 13, not 26, half the diameter, we use this formula, which gives us this. So that'll give us approximately 13 times 250, and this is going to be in terms of inches per minute. Okay, and now we got to convert that. So we end up multiplying it by 60, dividing it by 12 times 5280. And that's the same formula we have here, I think. 12 times 5280, 60, yep. Okay, so if we multiply all that out, we should get approximately the same answer. So 13 times 60 times 250 divided by 12 divided by 5280 pi. Now, what am I getting? 13 times 60 times 250 divided by, I'm getting 3 pi? Oh, they didn't, okay, so this gets me to V equals approximately 3.07765 pi, and then if we multiply that by pi, we get approximately V equals to 9.6687, and now we're miles per hour. Right? Because of this thing, it survived as miles per hour. Good. Questions? Okay, I got approximately 9.7. Same thing. Any questions? No? All right, let's take a break. Back in 10 minutes, we'll move on. Let's move on. Section 6.2. Again, this is an introduction to trigonometry. What is trigonometry? And for me, I like to present, or I like to go off on a little tangent that I think does a slightly better job, I guess, or just attempts to explain what the sine function is, and it's kind of built from there. So I know you've all had trigonometry, so you've already been working with the sine function for a while. But what is it? I don't know if you can. Some of you might have a good answer for that, but what is the sine function? So I want to try and explain what that is in a sort of holistic sort of way, just a sort of general guideline kind of way, without getting too mathy. but just kind of give an idea of what it is. And remember that this is not the work I'm about to do. It's not something that you're expected to produce on your own. It's just to kind of give you a sense of where this comes from and sort of what it means and sort of the birth of the study of trigonometry in my idea. Okay, so where did this come from? So long ago, some brilliant person, mathematician, on a Saturday night had nothing better to do than to think about the following kind of idea. What happens when we add numbers? Say we had 1 plus 2 plus 3 plus 4, right? And like, okay, let's say we add these forever. What do they add up to? Do they add up to something? Okay, so we add 1 plus 2, that's 3, plus 3, that's 6, plus 4, that's 10. Okay, so it's getting bigger and bigger and bigger. So clearly, whatever this summation is, it goes out to some positive number, some infinite number. Okay, nothing too special there. But then somebody thought, well, is it possible for us to come up with an infinite sum that does add up to some constant number, right? And so to do that, maybe somebody thought about this. Let's say we have a pizza, and on day number 1, we eat half the pizza. So this is half. And then on day number 2, we eat half of what was left over. So we take this leftovers and we eat half of that. So half of a half. So this is going to be 1/4 of the pizza. And then on the next day, we take half of what was left over, right? We just keep chopping it in half. So on this next day, we eat 1/8. And then if we keep going, let's come up with some other cool ink color. How about orange? Orange work? So then the next day, we eat half of that. And so now this day will be half of that, will be equal to 1/16. Okay, so if we start adding these fractions in that pattern, we see that we started out with 1/2, and then the next day we eat 1/4, and then the next day we eat 1/8, and then the next day we eat 1/16. So we start to see a pattern here. They're really powers of 2, right? So the next day it's going to be 1/32, and then, okay, theoretically we can keep going forever. We can always chop it in half and chop it in half. And I know that realistically that there comes a point where we can't chop it in half anymore, but mathematically we're able to do that. And so we can do this forever. And here is a sum that will go toward just 1, right? Because there's only 1 pizza at the end of the day. There's only 1 pizza. So here is an infinite sum that just goes to the number 1. Good. We're going to study this later on. I forgot what chapter it is in our book, but this is part of sequences and series. Let's see what chapter is that. Chapter 12, right? So this is what we're going to look at in like a couple of weeks now. So chapter 12. Chapter 12, sequences and series. Sequences and series. Okay. So I'm just giving you like a crash course kind of introduction to the idea. We'll come back and study this in a lot more detail in chapter 12. But for now, just this idea I think is fairly simple to get, right? We're looking for an infinite sum, and the ones that are interesting are sums that add up to some constant value, right? So which functions converge to something. All right, so then again, without really explaining where it comes from, some person out there, some brilliant person out there, was out there playing with various sort of various patterns. Like maybe they thought about this one, right? How about this one, where you take a number? Oh, okay, let's. How about this one was really the same thing as 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the 4th power plus 1 over 2 to the 5th power, right? That's what that one was, right? So why not think about different ones? How about 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial, right? Remember factorial, right, is the multiplication of all the integers down to 1. So 5 factorial equals to 5 times 4 times 3 times 2 times 1, right? It's this sort of countdown of multiplication down to 1. That's what that factorial means. Okay, so if we kept going on in this pattern forever, where does it lead to? Does it converge to some constant number? Does it go off to infinity? Right? So just interesting things to think about. And some brilliant person out there thought about, say, a pattern that was a little like this. How about 1 minus 1 cubed over 3 factorial plus 1 to the 5th power. Well, let's not do 1 then, because then, right, so let's, come on. Let's change this to the variable. We thought about this function. Let's have this function x, 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 a couple more x's here, x, x, where we're going to have this 5 factorial minus 7 over 7 factorial plus 9 over 9 factorial. I believe that's the formula. And they define this function. So let's call this f of x. And this goes on forever, right? Dot, 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 in the same pattern. So notice the pattern alternates from subtraction to addition, subtraction, addition, subtraction, addition, subtraction, addition. Whatever the input is goes into here. So whatever input value starts off with that input value minus that input cubed over 3 factorial plus that input 5 over 5 factorial. Okay, and again, there's no explanation to where this came from. Just an interesting property somebody thought about when in this world of infinite sums. So, for example, if that x value was, you know, the number, let's do the number 2. Let's say that value was 2. Then we would replace all those x values with a 2, and we'd have this minus this cubed over 3 factorial plus this to the 5th power over 5 factorial minus this to the 7th power over 7 factorial plus this to the 9th power over 9 factorial. So we see the pattern, minus, and then it keeps going forever. And so in this case, we have a 2 that we're replacing right in there. And then, you know, some cool math happens, and we try and figure out, does this converge to something? Does this infinite sum and difference of these, does this whole thing add up to some constant value? Okay, a lot of math happens there. You don't have to worry about that right now. I'm not trying to scare you with this. It's just something that works, right? So some mathematician figured this out, and he figured out that it does converge, and it converges to some number, and then we can figure out, you know, what kind of input values can we put into here. Instead of the 2, maybe we can put in a different value. Maybe it also works when we put in a 5. Let's put in a 5 in here. 5 in here, 5 in there, 5 in there, 5 in there, 5 in there. Okay, fine enough as it is, no problem. Okay, well, it turns out that someone really brilliant, I don't know how they made this connection, but somebody realized that there is a connection between this infinite sum, whatever this infinite sum is, and a right triangle. So they figured out that if we take a right triangle, so here is the right corner here, and we think of this angle theta right in there, whatever that angle theta is in there, in radians. Let's put it in radians, in rads, in radians. Good. And then we have some value here, which usually we think of this as the hypotenuse, and then opposite that, that's the opposite side, and then this is the adjacent side, right, adjacent to it. The ratio of opposite over hypotenuse, right, so if we actually take a measuring tape and measure this triangle and figure out this length there and divided by this length there, that it is equivalent to taking this angle and plugging it into this function. Good? Sort of, kind of, maybe? Good, 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 good. So in this case, if this is 5 rads, right, so from here, if this angle is 5 radians, right, in radians, if that's 5 rads of this triangle, and then we measure this distance here, you know, take an actual some way of measuring this thing here, and then measure this over here, the opposite side, and then measure the hypotenuse of it, then it turns out that the opposite side over hypotenuse is going to give you the result of plugging in f, this whole function in here, f, where we plug in a 5 into that. I don't know why. Some brilliant person figured this out. It's crazy. I don't know how. And it's not like we create, this isn't one of those things where humans invented this. This is one of those things where we discovered that this is the way the universe works. For some reason, there is this special relationship between the sides of a right triangle. This only works for a right triangle. If you don't have a right triangle, if we have some other triangle that is not a right triangle, then this whole thing doesn't work. This only works for right triangles. The opposite side divided by its hypotenuse happens to be equal to the result, the same result that you would get by plugging in the angle in radians into this crazy long formula. And as you might have guessed it, this function, we decided to call it the sine function. This is sine of 5.
Can't you divide like a non-right triangle into like 2 right triangles and then it'll
Sure.
work?
Sure. We can take any other triangle and then manipulate it and think about, well, what if we break it up and, you know, we have a right triangle, part of it is a right triangle, and then what's the other part? Okay. So we could do lots of geometry to fix it, but in terms of opposite over hypotenuse, it's got to be a right triangle. That ratio, right? So we'd have to do some geometric manipulation in order to work with other triangles. But the purpose, or as far as the definition of opposite of hypotenuse, it's got to be a right triangle when you do that little ratio.
Okay.
Okay.
Do you know when that like came about?
Ooh, no idea. That'd be good stuff to look up. You know, who created this? What kind of a brilliant person was thinking about this infinite sum, right? Where in the world did they realize that this infinite sum is somehow connected to dividing the opposite of hypotenuse of any right triangle, right? Like, who comes up with that? I have no idea. Weird, right? And this thing, well, you know, for the purposes of making trigonometry more accessible to people, right? We don't really think about this infinite sum when we first introduce trigonometry. We just make it a magical little button on your calculator. There's this magical little button on your calculator, and you hit sine and you put in the angle. This is what your calculator determines. Something along these lines. Not exactly. There's some other math that simplifies this whole thing, but essentially this is what your calculator is attacking. It's figuring out the infinite sum of this pattern, and that's how it gets that decimal answer. You know, when I first was going through trigonometry, that part bugged the heck out of me. Like, what is it doing? It's just this magical button on my calculator, and then somehow it's this little decimal answer. And like, how do I know what that is? Well, it's opposite or hypotenuse. Like, well, what the heck does that mean? So it just, to me, it felt like it was an inconclusive explanation. So I don't know. I hope this helps. Good. So then the formula for it can be written this way. I'll move it over here. Here is the formula for sine. Sine of x, where x is in radians. Make sure we put that in here. This is an angle in radians. An angle in radians is described to be this infinite pattern, right? Goes on forever, and we can describe that infinite pattern through this. This negative 1 to the n power will guarantee this alternating sine thing, right? And then x to the power of 2n plus 1 will give you all the odd ones. And then 2n plus 1 is in the denominator factorial. So this describes that. And that goes on forever, and that's what sine does. And someone just discovered that it happens to be connected to the division of the opposite over hypotenuse in a right triangle, right? So for example, if I have a right triangle and I measure this, and this is 7 feet, right? I get my little measuring stick, and I measure this is 7 feet, and I measure this, and this is 5 feet. And then I measure this. Well, I could measure it, but it also has to obey the pattern that this squared plus this squared equals that squared, right? So the hypotenuse h over there has to be that h squared must be equal to 7 squared plus 5 squared. So h squared must be equal to 49 plus 25. Good. So that must be h equals to the square root of 74. It's plus or minus when you take the square root, but we know that we're looking for a positive distance, so we can ignore the minus, right? So that must mean that this is square root of 74, which we can turn into a decimal, right? What's the square root of 74? Square root of 74 is 8.6 approximately. Oh, I lost it. 8.6023, I guess, approximately, feet. So if I took my measuring, some measuring tool, this would be approximately 8.6023 feet. This would be 5 feet. This would be 7 feet. And if I measure this angle here, and looking at this formula, they use the letter x. Usually we like to use theta, so it's the same thing. So this is x from in here in radians. So this angle right in there, whatever that angle is, must be the angle that satisfies this. So taking that x value, taking this guy right here, and taking that number, and then subtracting it and using this thing here. So it's got to be this number minus that number cubed over 3 factorial plus that number to the 5th power over 5 factorial minus that number to the 7th power over 7 factorial plus dot, 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 dot. That number, whatever that is, forever, that whole thing is equivalent to 5 divided by the square root of 74. Right? That's what this formula is telling me. That's pretty weird stuff. If I divide these two things, I'll get the same stuff. I'll get the same answer. Good? Questions, questions, questions? So 5 divided by that answer, it gives me, right, same as this. So I'm saying that 0.581238 this division is going to give me the same answer as this infinite sum when I plug in that angle in radians. Right, in radians. Good. Questions, 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 questions? As an idea, I hope this helps kind of visualize what sine is. Dot, 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 dot. And then this angle, whatever that angle is, these two things must be satisfied. Well, we have ourselves an equation. So if I know the opposite and the hypotenuse, I can plug it in, I get this, and then I have a way of solving for x, right? There's an equation. There must be some input value that makes that true. Good. Or the other way around, if I know the angle and I know, say, the 5, if I know this right-hand side and I know the 5, I can figure out the other one, right? So whenever you have an equation with three items, you can always solve for one of them if you know two of them. And you're like, well, how am I supposed to solve for x here? Well, that's hard without technology. 400 or 500 years ago, people did this by hand, right? Okay, now let's solve for x. This goes on forever. Let's solve for x. Let's figure out what is the angle that goes in here. Luckily for us, we reduced that down to just a button on our calculator. But the calculator, this is what it's solving, right? So when we hit sine inverse on our calculator, when we use those buttons, this is the type of thing that the calculator is solving for us. Good, sort of, kind of, maybe. Okay, and here's the one for cosine, very similar. Notice that the sine one has all these odd powers, power 1, power 3, power 5, power 7, whereas the cosine one has these even powers, 2, 4, 6, 8, right? It's an interesting pattern there. And so this is the one for the cosine one.
What does tangent have?
Well, tangent is a combination of sine and cosine. So I think we normally just go back to the easiest thing to do is to break it up into sine, cosine, and then work it out that way. And then you can also kind of go back to replacing this divided by that, and then using math to try and come up with a nice formula for it. But I don't want to go down that rabbit hole any more than I have to. I just wanted to give you some sense of what the sine function is, other than simply saying it's this cute little button on your calculator and don't worry about what it's doing. It gives you some sense. Although, of course, the math to actually do it is a little beyond us. But at least we have some sense, I hope, of what the sine function is and what the button is doing. Okay?
Before calculators, would people have to do that whole sine equation?
Yeah, isn't it crazy? Sure. Before calculators, how would people solve this? Well, at first, people actually solved it by hand. That's what it took to be a mathematician. Let's figure out what this is. Let's solve for x when this goes on forever and it equals some decimal over here. Okay, that didn't go far. That didn't take long for people to get frustrated with that. So then what do? Then you spend time coming up with shortcuts and patterns and approximations, right? Like, oh, this is basically, if we just go out 4 of these, that's pretty close, right? Do we really have to go out to infinity? Maybe we can just go out 4 of these and that makes it a pretty good guess. Okay, that's one way to simplify it. And then before calculators were invented, the invention that came right before that was scrolls and tables, right? So somebody figured out the answer for a bunch of them and wrote them down in a giant table somewhere, and then came out with scrolls. So scrolls were the calculators of their day. They would go out to the library and find the scroll that they needed that would help them solve certain things, and pull it out of the library, unroll it, unspool it all the way down to where they needed it to be, and looked up values like a giant table, written down in a scroll. That helps you simplify and not have to repeat things over and over again.
Okay. What about the abacus or the...
Right. So lots of technology that would help approximate things and simplify life a little bit. Same with calculators. Lots of stuff we do actually is an approximation rather than an exact answer. And so there's some math out there that helps simplify this ginormous infinite sum into something a little bit simpler to calculate, and then that's what your calculator does. and then it sacrifices some rounding issues. You know, maybe it only goes out to 10 decimals of accuracy, and for most people that's good enough. But if you really want to be extra accurate for some reason, then you would need a more powerful tool to be able to get a more precise answer. Good. Did you guys ever see that movie? What's the movie that's based on? What is it? Apollo 11? Apollo 11? Tom Hanks going to the moon, coming back. People saw that, right? It's what, from the 90s? It's pretty old now. Yeah, it's probably from the 90s. Anyway, the Apollo capsule that they experienced a I think it was an explosion in one of the oxygen tanks or something, and it threw them off course. And anyway, they had to calculate. They had to do some math to calculate their way back home, and they had to do it all by hand. I don't know if you ever saw that. That was a real life. It was a reenactment of a real life event there. So they literally sat down and figured out some of this math by hand because the computers of their time weren't able to calculate those things to the degree or to the accuracy that they needed. So, anyway, back to your standard sort of introduction of trigonometry. So I like to talk about that a little bit. I know that a lot of that math is still inaccessible, but I think that hopefully it gave you some sense, some idea of what a sine function is. But now let's go back to sort of the standard introduction of what it is. So trig is often explained in terms of the ratios that they're equivalent to rather than that infinite sum. So trigonometric ratios, special triangles, of course using your calculator, and some applications is what we'll go over. So there'll be a lot of definitions here. So this is usually what sine is defined to be for people. Consider a right triangle with angle theta, one of its acute angles. The trigonometric ratios are defined this way. So sine of theta is opposite over hypotenuse, cosine of theta is adjacent over hypotenuse, tangent of theta is opposite over adjacent, cosecant of theta is hypotenuse over opposite, secant of theta is hypotenuse over adjacent, and cotangent of theta is adjacent over opposite, right? Which is one way of describing it, but for me, when I was a student, it just kept bugging me, like, what is this weird notation, and who said it was equal to opposite of hypotenuse? And, just kind of got stuck with that. But anyway, okay, hopefully we have a slightly better understanding of what this means. Good. So remember, it's got to be for a right triangle. Good. Okay, so that's pretty standard, I think. So the symbols we use for these ratios or abbreviations for the full names are sine, cosine, tangent, cosecant, secant, and cotangent. Right? I think all of this is pretty familiar. Since any two right triangles with angle theta are similar, these ratios are the same. So regardless of the size of the triangle, the trigonometric ratios depend only on theta. Good. So sine of theta is opposite over hypotenuse, that's 3/5. But if we have a bigger triangle that is a similar triangle, it has the same angle theta, then opposite over hypotenuse would still be the equivalent ratio of 3/5. Good. So if we were given any random triangle like this and we wanted to figure out the 6 trigonometric ratios, then all we have to do is think about the sine of theta is opposite over hypotenuse. Sine of theta would be 3/2. Cosine of theta is adjacent over hypotenuse, so it would be √5/3, right? And so on and so forth. Let's see them down here. Sine of theta is 2/3. Cosine of theta is √5/3. Pretty straightforward, right? Any questions? Questions? Okay. There's different approaches to memorizing these things. But I favor I favor memorizing some basic shapes that give you the standard angles that we often use. Good. So there's some special ones that will give us the results we want. So I know that some of you in your trig classes maybe memorized the unit circle with like the standard angles in the unit circle. And I mean, I guess that's fine. If you have a great memory, then sure. But it just feels, I have a terrible memory, so I like to, not waste my capacity to memorize things on whenever I can avoid it. So all you need to do is think about two general shapes. One of them is going to be a square that has length 1 all the way around, and a triangle, equilateral triangle, that has sides 2 all the way around, right? It's equilateral, so all the lengths are side 2. Okay. In a square, all of these are 90 degrees. 90 degrees, 90 degrees, 90 degrees, right? Okay, so what we're going to do is we're going to take a square and we're going to cut it straight across like that to make a triangle. Okay, and then we're going to figure out that side there, H. Okay, the triangle, okay, remember that the hypotenuse, that 1 squared plus 1 squared must be equal to h squared. Pythagorean theorem tells us that. Very useful. So that's going to mean that 1 plus 1 is 2. 2 equals h squared. So therefore, the square root of 2 equals to h. Technically plus or minus, but we know for sure h has to be positive. So we have that this is root 2. Good. And now this is 90 degrees here, and this was 90, so that means that each one of these corners must be 45 degrees. All right, so this got kind of messy, so I'm just going to simplify it and bring it out and say that it's this triangle, this green triangle. Sorry about my drawing skills, but it's this triangle that looks like this. It's got 90 degrees there. It's got 45 degrees there. Another 45 degrees here. The hypotenuse is root 2, and this is 1, and this is 1. From here, we can get all of the trigonometric functions involving 45 degrees. Sine of 45 degrees is 1 over root 2. Cosine of 45 degrees is 1 over root 2. Tangent of 45 degrees is opposite over adjacent. It's 1 over 1. Good. So we can find all the standard trigonometric ratios involving 45 degrees. And all we have to do is think of a square that involves 1, 1, 1, with sides 1. Good. We're going to do this similar kind of thing with this triangle, an equilateral triangle where all the sides are length 2. Square with all sides 1, a triangle with all sides 2. We bring this down, right, like you guys had mentioned earlier. If it's not a right triangle, we can make it a right triangle. We can drop that line there, and that would be H, and that forces that to be a right triangle. Okay, before I had done that, it's an equilateral triangle, which means that all of these guys were 60 degrees. Right, an equilateral triangle where all of these guys are 60 degrees. And this guy used to be 60 degrees, but then if I chop it in half, and I know this doesn't look quite right, but if we chop it in half, that must mean that this side right here, from there to there, must be 30 degrees. Good. And then if we chop this right in half, this whole side was 2, therefore this side must be 1, and this side must be 1. Maybe it takes a little bit of geometry to convince people that that's true, but hopefully you've had a little bit of geometry and you're okay with that. I don't really want to go down the rabbit hole of that. But it sort of makes sense, I think, if we bring this down, that it should be 30 degrees here and 30 degrees there. Good. Okay, so and next we can find the value of h. So h must be that 1 squared plus h squared equals to 2 squared. So 1 plus h squared must be equal to 4. So h squared must be equal to 3, and so h must be root 3. Good. Plus or minus, but again, we're looking for a positive one. So this must be root 3. I know, it got kind of messy again, so I'm going to redraw it again down here with just the parts that I want. So I end up with this triangle that comes down here like this. This side is 1, right, because it's half of the 2. This side is root degrees, and this side is 30 degrees. Right, so we can derive this triangle from this very basic shape. And from this very basic triangle, we can get all of the standard trigonometric functions that involve 30 degrees or 60 degrees. Right? So for example, sine of 60 degrees is opposite over hypotenuse. So sine of 60 equals root 3 over 2. Sine of 30 degrees is 1/2, opposite over hypotenuse. So we can derive all of them from there. Any questions? No? No? Okay, so let's go back over here. This is the same thing they did. We have a square where all the sides are 1. We can go right across, chop it up. We get 45, 45, 1, 1, and then we can solve for the root 2. And then we got all the ratios involving 45. We can do the same thing with an equilateral triangle. All the sides are 2. That must mean that this side is 1. We can solve for the hypotenuse, not the hypotenuse, the height of this triangle, which is root 3. And then here we have a triangle that will give us all the values for 30 or 60 degrees. Right, so here they are side by side in terms of degrees. And from there, we can come up with this giant table where, depending on the degree, 0, 30, 45, or 60, and then we can get all the sines, cosines, tangents, cosecants, secants, cotangents, everything we want out of staring at these 2 triangles. Good. It makes more intuitive sense to think of them in degrees, but then we can easily convert those degrees into radians. And then again, staring at the same triangles, we can get all of these common ratios. So, like I said, I know that maybe some of you guys were just forced to memorize this table. Wow, sorry, you've been traumatized. Did a previous math teacher hurt you? There's no real need to memorize it. It's just a real simple triangle over here. You can just make your little triangle on the side of any exercise you're working with and get all those values, right? There's no real reason to, I don't know, just memorize all of that out of brute force. Anyway, any questions? No? And then, of course, we can always just use our calculator to find any of these things. Right, so mathematical methods called numerical methods used in finding trigonometric ratios are programmed directly into scientific calculators. Right, so that infinite sum that I described, that's not exactly what's in your calculator. We've come up with some other sophisticated math to find equivalent values that are easier to find, or in some cases, like a good approximation that makes it easier for your calculator to find it. But essentially, they're finding that infinite sum. It's just something equivalent that's a little easier for your calculator to determine. So then, the benefit for us is that we have a nice, pretty button on our calculator that gives us those results. Okay. So, for instance, sine of 1 means that means the sine of an angle whose radian measures 1. So we can use our calculator to find these things. And it's very, very important that you make sure that your calculator is either in radian mode or degree mode, because we'll get very different answers, right? When we have 1 radian, that's a pretty big angle. Remember that in radians, 2 pi is an entire circle. That means pi is half a circle. Pi is 3.14. This is 1/6 of a circle is 1 radian. Right? That's an angle that's about 1/6 That's pretty close, one rating, approximately 1/6. It's a little bit off than that because it's 1 over 6.28. So it's approximately 1/6. This is approximately 60 degrees. So it's pretty big. Whereas 1 degree is 1/360th of a full rotation. That's actually pretty small. So you get very, very different answers. So make sure that your calculator is in the correct mode. And we'll use our calculator now to be able to figure out some of these things. Okay, so tangent of 40 degrees, cosine of 20 degrees, cotangent of 14 degrees, and cosecant of 80 degrees. Okay, so tangent of 40 degrees. Let's go to our calculator. Okay, so the first thing we want to do is go over to where it says mode. So right over here, mode. And then we want to make sure that we are in either radians or degrees. That's this right here. Right now I'm in radians. So if I go down, down, and go over to the right and hit enter, now the degrees will be highlighted, and now I'm in degrees. Okay, so now I get to get out of here, hit quit. So second, quit. And now I'm ready to figure out some of these things. So tangent is this nice pretty little button here. Tangent of 40, and I'm already in degrees. So that'll give me the answer I want. That easy. Good. Cosine, cosine of 20 degrees gives me that answer right there. .83, .93. Yep, we get these two. Good, 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 good. Questions, 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 questions. Now for cotangent, cosecant, we don't have a nice easy button on our calculator. Right? There is no button that says cotangent and cosecant. Good. But we have to know the relationship between tangent and cotangent to be able to solve for part C. So for part C, we have to know that let's see, that cotangent of 14 degrees is equivalent to 1 over tangent of 14 degrees. Right, so then we can just figure out what tangent of 14 degrees is and do 1 divided by that on our calculator, and we'll get our answer from there. And for D, we need to know that cosecant of 80 degrees is equal to 1 over sine of 80 degrees. And we get our answer from there. Good, 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 good. Okay, so tangent of 14 degrees, tangent of 14 degrees gets me that decimal, and then 1 divided by that decimal gets me a little bit over 4 for part C. And then sine of 80 degrees is equal to that, and then 1 divided by that previous answer is going to give me the 1.015 ... Good. And let's make sure that that matches with these answers. So that's how we get that. Any questions? Good, good, good. Sort of, kind of. Applications of trigonometric right triangles. Okay, so to solve a triangle means to determine all of its parts from the information known. So you got to find all the interior angles and all 3 sides given the information provided. So here's an example of something that might say solve this triangle. They only gave us the hypotenuse and 1 angle, but from here we can figure out everything else. So, for example, we can use the property that sine of 30 degrees is equal to a over 12. So 12 times sine of 30 degrees must be A. That's how we can find A. Sine of 30 degrees, going back to our standard triangles, this is 60, this is 30, this is 1, this is 2, this is root 3. Sine is opposite over hypotenuse, so I know that this is equal to 1/2 times 12 equals to A, so 6 must be equal to A. There, I found one of them. Good. B, well, I can use cosine of 30 degrees. Cosine of 30 degrees is equal to adjacent over hypotenuse. So 12 times cosine of 30 degrees must be B. And from my triangle here, cosine is adjacent over hypotenuse. So this must be root 3 over 2 times 12 equals to B. So therefore, B must be equal to 6 root 3. 6 root 3. And then knowing that the sum of the interior angles of a triangle must add up to 180. If this is angle, I don't want to say angle B. It's angle capital B. Come on. Angle capital B. It must be true that 30 degrees plus angle capital B. I guess maybe I could do angle capital B. Plus the 90 degrees, which is this guy, must add up to 180. Right? So from there I can see that this must be 60 degrees. 30, 60, 90 degrees. Good? Questions, questions, questions? And so I've solved the triangle. I found all the interior angles and I found all 3 sides. It's not the only way to solve it. You can also think about using the other properties, tangent, cotangent, stuff like that. So we got that, and let's look at another application here. Let's say we look at the angle of elevation is described from the horizon going up is the angle of elevation. From the horizon looking down is angle of depression. So keeping that in mind. If an object is being observed is above the horizon, then the angle between the line of sight and the horizon is the angle of elevation. If the object is below the horizontal, then the angle between the line of sight and the horizontal is the angle of depression. Okay, so then keeping that in mind, a giant redwood tree casts a shadow of 532 feet long. Find the height of the tree if the angle of elevation of the sun is 25.7 degrees. Okay, just like the picture describes, here is the horizontal, and then we go up by 25.7 degrees. That's why it's called the angle of elevation. So that always gets confusing. But luckily this comes with a nice picture for us to make sure we don't confuse it. Okay, so basically we have this triangle. This whole thing kind of simplifies to having a triangle that has angle 25.7 degrees, and when we have h over there, and then we have 532 feet there. Find the height of the tree. Okay, without simple. So if I use sine, I would need h over this distance, which they didn't give us, right? This is my right triangle here. So the only other function that combines these two would be tangent, right? So I want to say that tangent of 25.7 degrees must be equal to opposite over adjacent, h over 532. So 532 times tangent of 25.7 degrees is equal to h. And now that's just some pretty little button on my calculator. I don't have to worry about what the actual calculation of that is. So I know that's going to be this infinite sum thing that's really crazy to figure out. But we can just type in this. Just make sure that you're in the correct setting, so they're in degrees. That gives you that. So I know that that infinite sum thing is going to be this decimal, 0.2813, 4813, let's say. 0.4813 approximately. So it's almost half. So that means it's going to be a little bit less than half of that. 532 is going to be the h. Good. So multiply that previous value times 532. So I can just type in the whole thing. 532 times tangent of 25.7, and I get 256.03. feet. Always come back and see if it sort of makes sense, given the picture, if you get something that sort of made sense. If you got, a ridiculous answer, like a negative answer or a decimal answer, it just wouldn't make sense to the values that you were expecting. So, yep, the author solved it in the exact same way, and they got approximately the same answer. Any questions? No. All right, this is a good place to stop. We're done with 6.2. Reminder that next week, Wednesday, will be our next test. I'll send out an email today. It will cover up to chapter 4, the sections we did. So it's the last 2 sections of chapter 2, the sections in chapter 3 that we did. Again, we didn't do them all. And then the sections of chapter 4 that we did. I've updated the homework assignment to show that we've skipped a couple sections, so reference that. Also, I'll send out an email to point out which sections will be on the test. So to prepare for the test, you should complete the homework as much as you can. The test will be questions that are inspired by those questions in the homework. The homework will be due on Wednesday at 8 a.m. to get full credit. So you'll submit that to the Gmail account, and then we'll have class like normal on Wednesday. We will finish around 11, and that's when the test will become available, and you have all day Wednesday, all night, and then you could turn it in by Thursday morning at 8 a.m. or any time before 8 a.m. Thursday in order to get full credit. Any questions about that?
For the homework for today,
yes.
Is that already posted, or were you?
If I'm not mistaken, yes. That sheet that I posted should already have the homework assignments for all the sections we're going to be doing, for the whole 4-week period that we have left. So I think in the assignment, it automatically skips to chapter 6. So there's some questions from chapter 6 already. And then next, we're going to go back to chapter 5 and again reintroduce trigonometry from a different perspective.
Okay, cool.
Good.
Thank you.
Any questions from anyone? All right, I'll see you on Monday. Have a fantastic weekend. Stay safe out there.
Thank you.